Earth makes one complete orbit around the Sun approximately every 365 days, giving us our year. This tilted orbit, combined with Earth's axial tilt, also gives us our seasons. And while we're talking about orbits, don't forget our constant companion, the Moon, which orbits Earth, influencing our tides and illuminating our night sky. This intricate ballet of celestial bodies is a testament to the elegant mechanics of gravity. Think of gravity as the universe's glue. Our Sun, being incredibly massive, holds all the planets in our solar system in its gravitational embrace, including Earth. Let's start with what we know best, our own backyard. It's governed by a powerful invisible force, gravity, Earth's orbit, and the solar system. Visuals. Look at our home. But what if I told you that our entire world, this incredible planet we call Earth, is but a tiny, insignificant speck in the grand tapestry of the cosmos? Beyond our solar system, stars and galaxies. Visuals. Pan out further from the solar system, revealing countless stars. Then a beautiful shot of the Milky Way galaxy. 3. The vastness of space, distance and light years. Visuals. Graphic showing light years as a unit of distance. Examples of distances in light years, e.g. nearest star, Andromeda galaxy. When we talk about these astronomical distances, our usual units of measurement, miles or kilometers, become utterly meaningless. Instead, astronomers use a unit called the light year. A light year is the distance light travels in one Earth year. Light, the fastest thing we know, zips along at roughly 186,000 miles per second, or nearly 300,000 kilometers per second. So 1 light year is about 6 trillion miles, or 9.5 trillion kilometers. The Big Bang and expanding universe. Visuals. Animation of the Big Bang, then an expanding balloon analogy. So how did all this begin? The prevailing scientific theory is the Big Bang. About 13.8 billion years ago, the entire observable universe was incredibly hot and dense, contained in a singularity. Then it began to expand. Not explode into existing space, but rather space itself expanded. And it's still expanding. Imagine blowing up a balloon with dots on its surface. As the balloon inflates, the dots move further apart from each other. This is a simplified analogy for how galaxies are moving away from each other as the universe expands. This expansion is accelerating, driven by a mysterious force called dark energy, which we'll touch on briefly. The Big Bang theory is supported by a wealth of evidence, including the cosmic microwave background radiation, the faint afterglow of the early universe, and the observed redshift of distant galaxies, indicating they are moving away from us. 5. Cosmic ingredients. Matter, and dark energy. Dark matter, making up about 27%, doesn't emit, absorb, or reflect light, making it invisible to our telescopes. We know it exists because of its gravitational effects. It helps hold galaxies together, and its presence is necessary to explain how galaxies rotate and cluster. Scientists are actively searching for particles that could make up dark matter. The remaining 95% is composed of 2 enigmatic components, dark matter and dark energy. When we look out at the universe, we see stars, planets, galaxies, what we call normal matter. But astonishingly, normal matter makes up only about 5% of the universe's total mass energy content. Dark energy, the most mysterious of all, accounts for about 68% of the universe. It's the force driving the accelerating expansion of the universe. We don't fully understand what it is, but without it, the expansion wouldn't be accelerating as observed. These dark components represent some of the biggest unsolved mysteries in modern astronomy. Beyond stars and galaxies, the universe is filled with a dazzling array of cosmic wonders. We have nebulae, vast clouds of gas and dust where new stars are born. These stellar nurseries are often incredibly beautiful, glowing with vibrant colors. Celestial objects and phenomena. Visuals. Quick montage of various celestial objects, nebulae, star-forming regions, supernovae, exploding stars, black holes, accretion disk animation, neutron stars, quasars. Make sure you like and subscribe to our channel Castro Into Space Videos. You'll see more of these scientific videos in the future. The orbiting donut. Visuals. Our first stop, Earth orbit. Let's say we've engineered a perfect frictionless launch. Our donut, let's call him Donut Knot, reaches a stable orbit. What then? Firstly, it would be in a perpetual state of freefall. No more gravity pulling it down. Donut Knot would simply float, eternally circling our planet. The view I imagine would be spectacular. Now I know what you're thinking. A donut? Isn't space exploration about cutting-edge science and understanding the universe? And yes, of course it is. But sometimes the most unexpected thought experiments can reveal surprising insights, or at the very least, provide a delicious excuse to think about physics. So let's hypothetically launch our intrepid, sugary subject beyond Earth's atmosphere. What cosmic fate awaits our humble donut? Firstly, it would be in a perpetual state of freefall. No more gravity pulling it down. Donut Knot would simply float, eternally circling our planet. The view I imagine would be spectacular, but then the challenges begin. The vacuum of space. The absence of air pressure would cause any water content in the donut to rapidly sublimate or turn directly from ice to vapor. Our soft, fluffy treat would become dry, brittle, and likely shatter at the slightest touch. The glaze, it might crystallize or flake off as its moisture content vanishes. It wouldn't be edible for long. And what about temperature? In direct sunlight, one side of Donut Knot would bake, while the other side, exposed to the cold void, would freeze. Without an atmosphere to distribute heat, temperature extremes would be brutal. Our donut would be a sad, desiccated, half-baked, half-frozen husk space dust particle with a puff of donut dust. Maybe a graphic of the asteroid belt. Imagine Donut Knot drifting through the asteroid belt. While Hollywood often depicts these as dense fields of tumbling rocks, they're actually vast and mostly empty. Still, the statistical chance of impact, however small, increases with distance and time. One unlucky encounter and our donut would meet a spectacularly messy end. But what if, by some miracle, Donut Knot survived the solar system and drifted into interstellar space? This is where things get truly mind-boggling. The emptiness of interstellar space is almost incomprehensible. The average density of matter is incredibly low, a few atoms per cubic centimeter. Our donut would continue its lonely, silent journey for millions, even billions of years. While sending a donut into space might seem like a silly idea, it helps us appreciate the delicate balance that allows life to thrive on Earth and the profound, relentless forces at play across the universe. It shows us that even the simplest objects obey the complex laws of physics. So next time you enjoy a donut, perhaps spare a thought for its potential cosmic journey. Just be glad it's not facing the vacuum of space, micrometeoroids, or billions of years of radiation, because for now its destiny is far more delicious. The scariest thing about dark matter is that it makes up about 27% of the universe, yet it doesn't interact with light or any other form of electromagnetic radiation. This means it's utterly invisible, undetectable by any of our instruments that rely on light, and it passes right through us, through our planet, and through everything we know, without us ever feeling its presence or even knowing it's there. It's a vast, unseen, pervasive scaffolding holding the universe together, an undeniable force that we cannot see, touch, or directly observe, fundamentally shaping the cosmos without us ever truly interacting with it.